We all know that feeling. You're standing in the kitchen or sitting in the living room, and suddenly everything goes dark. A type of silence that creeps over the house and is more intrusive than the sound it replaced. The silence of a power outage. All of us have experience with power outages, usually multiple times per year. Sometimes only for a few seconds, sometimes longer. Can you imagine the silence if you went to check your phone following the lights going out and your phone was also dead? What if the same for every electronic device? Your phone, your computer, your car, your backup generator, everything. This is the scenario we're going to cover in this essay. An electromagnetic pulse, or EMP, is a burst of electromagnetic energy that is capable of inducing currents in electronics that are not hardened against it. EMPs can be generated naturally through intense solar radiation or artificially, primarily through the use of nuclear weapons. EMPs can significantly damage all infrastructure, including power infrastructure, over an extremely wide area, leading to extended blackouts in some real apocalyptic scenarios. It should be no surprise we're covering this topic in the How This Ends series. A nuclear EMP is produced when a nuclear explosion releases a flood of gamma rays that interact with the upper atmosphere. These gamma rays knock electrons from air molecules through a phenomenon known as the Compton effect. This moving cloud of high-energy free electrons generates an intense electromagnetic field that rises to a peak within nanoseconds. Atmospheric nuclear explosions yield a much more effective EMP than those detonated on the ground. A high-altitude EMP, also known as HEMP or HEMP, from a nuclear explosion has three distinct components: E1 for early time, E2, which is the intermediate time, and E3, which is late time. These have different physical origins, durations, and impacts on electrical systems, including the electrical grid. The early time, or E1 component, is an extremely fast, high-energy pulse with a total duration of only tens to hundreds of nanoseconds. The frequency of this component results in it mainly affecting relatively short conductors, small antennas, and electronic circuitry. This includes microprocessors, which are in pretty much every electronic device you can think of. From a perspective of the power grid, this could damage the sensors, protective relays, communication equipment, and processors that the Supervisory Control and Data Acquisition System, or SCADA, is comprised of. SCADA is a collection of standardized equipment that provides remote monitoring and control features that are integral in keeping the electric grid operating. The heart of this system is a networked collection of microprocessors that are similar to what is found in a desktop computer. Without SCADA, not only would the automated protection functions that keep the grid operational fail, but the grid operators themselves would lose oversight as to the condition of the grid or where issues exist. The intermediate time E2 component of an EMP is considered the least dangerous, at least from a power grid perspective. E2 is sometimes described as thousands to millions of simultaneous lightning strikes occurring over a large area. The electric grid already has extensive protections against lightning strikes. However, if the earlier E1 pulse damages devices such as lightning arresters, surge protectors, or grounding equipment, the damage caused by E2 could be significant, especially to large power transformers. The late time E3 component is a very slow, long duration pulse lasting several seconds to minutes. E3 is caused by the interaction between the high altitude nuclear fireballs expanding plasma in the Earth's magnetic field, creating what is known as a magnetohydrodynamic disturbance, or MHD. This can induce massive currents, especially in long conductors like the ones that cover our landscape and compose the transmission and distribution systems of the power grid. As we discussed briefly in the essay on physical attacks on the grid, the most important and difficult to replace components of the grid are the large, high-power transformers. The currents generated by the late time component are much different than those that these transformers are designed and protected from, and as such, these transformers can immediately develop hotspots and degraded insulation that leads to a failure. The impact of the late time component of an EMP is similar to that of geomagnetic storms. The impact from geomagnetic storms is well known. In 1989, a geomagnetic storm caused the collapse of the Hydro-Quebec power grid in under 2 minutes, resulting in the loss of power for more than 6 million people for 9 hours. The specific cause was the failure of voltage reactive compensators that tripped due to an increase in line harmonics, which caused a voltage collapse and frequency increase. The rest of the grid soon collapsed due to the abrupt loss of load and generation. Another example is what is known as the Railroad Storm, or sometimes the Great Geomagnetic Storm of 1921. On May 15, 1921, a telegraph exchange in Sweden burst into flames. Soon after, the same thing happened in Brewster, New York, at a railroad switchboard. An aurora was seen as far south as Texas. Over 85 years before the world's first nuclear bomb was detonated, the Earth experienced an extremely powerful geomagnetic storm known as the Carrington event. This 1859 geomagnetic storm is the strongest on record. Given the lack of electrical systems at the time, there was a minimum impact on civilization. However, many telegraph systems were damaged. Experts have widely speculated that if another Carrington-level event were to occur today, there would be regional power outages, changes to satellite orbits, and substantial impacts on radio-based technologies. This speculation was almost a reality on July 23, 2012, when a coronal mass ejection, roughly the magnitude of the one which caused the Carrington event, crossed Earth's orbital path. However, the Earth had missed it by about 9 days. Given how likely these things occur, this is one of those things where it's more of a question of when rather than if it will occur. So back to nuclear EMPs. The area of effect of a high-altitude EMP caused by a nuclear detonation in the atmosphere can be millions of square kilometers, potentially covering most of the continental United States, causing a nationwide power grid collapse. There's really no good frame of reference for how long a massive outage like this would last. Estimates are from months to years. Every industry and utility relies on the power grid, such as water supply and wastewater treatment, traffic control, oil and gas delivery, transportation of food and other necessities, and all other commodities which make modern civilization possible. There are some real-life examples of EMPs caused by high-altitude nuclear detonations, such as Starfish Prime in the Soviet K project tests. Starfish Prime was a test carried out by the United States in 1962 using a small, by today's standards, nuclear explosion, 1.45 megatons, detonated approximately 400 kilometers above the Pacific. This created an EMP that knocked out about 300 streetlights in Honolulu and cut off some telephone communications and triggered burglar alarms. This was a relatively small bomb exploded over the ocean at a time before the rise of digital electronics and the prevalence of the microprocessor. The Soviet Union likewise conducted several high-altitude nuclear tests in Kazakhstan during the early 1960s. Notably, Test 184 in October of 1962, Soviet scientists ran a 350-mile telephone wire to record the impact of the EMP. Every fuse placed in line blew, and the wire melted through its entire length. Additionally, a power plant about 400 miles away burned down, and 600 miles of buried power cables were burned out. The bombs used for this test were even smaller than Starfish Prime, at about 300 kilotons. We know this information because it was leaked in 1991 after the collapse of the Soviet Union. A relatively small nuclear explosion in high altitude can knock out the power for millions of people for an extended period of time. This would result in the immediate collapse of modern civilization for those impacted, and most of the people in the affected area would be at real risk of death from starvation, disease, and lack of water and medicine. One of the more frightening aspects of knowing the damage an EMP could cause is how it changes one's understanding of what actors are threats. Traditionally, as an American living in the continental United States, if one were asked about threats from foreign adversaries, the immediate response would be the large militaries of the world, such as Russia and China. However, it is possible that small nations, rogue nation states such as North Korea, or even terror organizations could acquire and possess the means of causing mass casualties to American society through a high altitude nuclear explosion that causes an EMP. This isn't just speculation on my part either. As part of the annual National Defense Authorization Act for fiscal year 2001, so this is actually before 9/11, believe it or not, the United States Congress established the EMP Commission to assess the threat to the United States from an EMP attack. This commission was to assess potential EMP threats, evaluate the vulnerabilities to military and civilian systems, assess the recovery and repair capabilities, and the feasibility of protective measures. An executive report was published in 2004, and a comprehensive analysis was published in 2008. The commission was then disbanded, but reauthorized by Congress again in 2016, and several more reports were published between 2017 and 2019. I plan to cover these reports more fully in future essays or the longer form of this essay, but for now I'll summarize some of the key findings. The E1 and E3 components of an EMP would cause simultaneous failures across the grid, leading to a system collapse and widespread blackouts. The loss of SCADA systems would significantly hinder restoration efforts. High voltage transformers are particularly at risk. These critical components can have a lead time measured in years. Restoration is measured in at least months, but could easily extend into years depending on the severity and location of the EMP. Telecommunication networks underpin multiple facets of modern society: commerce, emergency services, national defense, and daily personal communications. Traditional landline, mobile networks, satellite communications, and then the backbone of the internet, routers, switches, etc., will all be significantly impacted by an EMP. Similar to the power industry, the oil and gas industry relies on SCADA systems to monitor and control industrial processes. Production, transportation, especially via pipelines, and refining of petroleum products would be impacted, which has obvious downstream effects on restoration and survival efforts. Transportation systems such as air traffic control, cargo shipping and port operations, rail services and control centers, commercial trucking and traffic management systems, public transit, and personal vehicles are all vulnerable to an EMP. In terms of the food system, agricultural production, processing, storage, and distribution are all severely limited during an EMP event. So how real is this risk? Well, for starters, many nations do not view an EMP as an attack on the same scale as a direct nuclear attack, even if the EMP is caused by high-altitude nuclear detonation. Russia and China, for example, seem to have the doctrine that a nuclear EMP is in the category of information warfare, a spectrum that includes things like cyber attacks, more so than a physical attack like conventional bombing. The chairman of the EMP Commission, Dr. William Graham, warned Congress that, quote, an EMP attack might be made by a North Korean satellite right now. A super EMP weapon could be relatively small and lightweight, and could fit inside North Korea's KMS-3 and KMS-4 satellites. These two satellites presently orbit over the United States. The south polar trajectory of KMS-3 and KMS-4 evades U.S. ballistic missile defenses, resembling a Russian secret weapon developed during the Cold War called the Fractional Orbital Bombardment System, or FOBS, that would have used a nuclear-armed satellite to make a surprise EMP on the United States. End quote. I focused on North Korea because they are a known rogue nation that is often not thought of as a real danger, at least to most NATO countries. However, this EMP capability makes them just as much as a threat as any other nation. The solution to this problem needs to look something like this: grid hardening and storing of 1-1 replacements for most critical power transformers, making plans for large-scale outages and how we're going to address them, as well as deterrence and prevention. Unfortunately, our government does not seem to be moving in that direction, at least not quickly. Back in August of 2021, Michael Mabee filed a complaint with the Federal Energy Regulatory Commission, or FERC, about the reliance on China in manufacturing the large transformers that make up the bulk power system. This complaint was centered around the fact that the grid relies heavily on Chinese manufactured equipment with no mandatory security checks, leaving the grid vulnerable to external influence. His concern was centered around an event in 2019 in which a large power transformer imported from China was seized at the Port of Houston and sent to Sandia National Laboratories, where hardware was found that allowed remote disabling of the transformer. The complaint requested that FERC survey and document the quantity of Chinese-made equipment already in use and implement new reliability standards that includes inspections and testing to ensure remote operation of the device is not installed. In October 2024, FERC denied this complaint and continued to ignore this threat. There are many other examples of officials and agencies choosing to look away and pretending that this threat does not exist. I could probably do another several articles just on these failures. Maybe I will. But for now, I think I made my point. An EMP is a real threat, and it would impact every utility, institution, and piece of infrastructure that makes modern civilization possible. This essay is a part of the latest collection I'm working on, which covers the fragility of the modern electrical grid, as part of the How This Ends series, in which I research and write about issues that are capable of forming cracks in our civilization. If you like this, check out my other work, follow, leave a comment, and subscribe as I have many more planned. Thanks for listening. Until next time.